Hi everyone! So today we're going to be going over how to rank the acidity of alpha hydrogens. This is something that you're going to see a lot in chapter 22, so let's first just go over what alpha hydrogens are. So alpha hydrogens are hydrogens that are one carbon away from a carbonyl carbon. So say here we have a carbonyl, and alpha hydrogen are just these hydrogens that are one carbon away from our carbonyl carbon. These hydrogens can actually be abstracted by bases, which remember, bases are proton acceptors. Protons are just the same thing as hydrogens without their electrons. And acids are proton donors. So what our base will do is it'll use its lone pair of electrons to go out and grab a proton, a hydrogen. And then the electrons left between hydrogen and carbon are going to stay there. So that carbon is going to be left with a negative charge. This negatively charged carbon is actually a good nucleophile and it can attack electrophiles. You'll see a lot of reactions in chapter 22 in which an alpha hydrogen is abstracted, and that carbon, that negatively charged carbon, is a good nucleophile. An example of this type of reaction is when a negatively charged carbon attacks an alkyl halide. So what will happen is our negatively charged carbon will attach to the carbon where our halogen is, kicking off our halogen, our bromine, and you'll see that added to our compound is this CH2CH3 group from our alkyl halide. On your exam, you're going to be given different carbonyls that all have alpha hydrogens, and you'll be asked to rank the acidities of these alpha hydrogens. So let's go over some quick acidity rules. So I've written out a guide for you guys as to how to rank by acidity, but let's just review the basics. When we rank by acidity, we're really ranking by stability of the conjugate base, which is the acid after it's donated its proton and is left with a negative charge. The more stable our conjugate base is, the more willing our acid will be to donate its proton. Feel free to look over these rules on your own, and I'll explain them more in depth in our practice question. So let's say we have a question here that's asking for us to rank all of these molecules by their acidities. The first step for any ranking by acidity question is drawing the conjugate base of all of these molecules. So all these molecules after they've lost a hydrogen and they're left with a negative charge. Something that I see here though is that all of our molecules have a lot of hydrogens on them. So how do I decide which hydrogen on each molecule to deprotonate? Well, I'm going to deprotonate the hydrogen on each molecule whose conjugate base is the most stable. Resonance is actually something that can make our conjugate base very stable because resonance is a delocalization of charge. More delocalized charges are more spread out charges, and more spread out charges are more stable. So for example, let's look at this molecule on the very left. If I were to deprotonate this hydrogen, this alpha hydrogen in the middle of these two carbonyls, let's look at what that conjugate base looks like. So this conjugate base is actually a very stable conjugate base compared to if we were to deprotonate the hydrogen on this side or on this side, because it can resonate across two oxygens. And I'll show you what that resonance looks like. So it could resonate to the oxygen on the left, or it could also do the same thing to the oxygen on the right. It could resonate to the oxygen on the right. So I picked the place to deprotonate that had the most resonance. So I'm going to do the same thing for all these other molecules, and then we'll come back to the question. So I've drawn all these molecules' conjugate bases along with their resonance structures. Earlier I was talking about how conjugate bases that can resonate more are more stable. So out of all these conjugate bases, the ones that have the most resonance structures are going to be our more acidic molecules. So let's count how many resonance structures all these conjugate bases have. These two right here have 3 resonance structures. All these others though, they only have 2 resonance structures. So because of that, the charge is not as delocalized, so it's not as stable. So I'm going to say that these two are going to be our top ones. They're going to be 1 and 2, and these are going to be 3, 4, and 5. Now we can move on to our other acidity rules. The next rule for ranking by acidity is to look at the atom or atoms carrying the negative charge, because atoms going down and to the right on the periodic table carry negative charge better, since they're both more electronegative and larger. So let's look at all these atoms. So let's say, we know that these are going to be 1 and 2. On this molecule, the negative charge is carried on 1 carbon and 2 oxygens. On this molecule, also, our negative charge is carried on 1 carbon and 2 oxygens. So we can't use the atom rule when ranking these two molecules. Same with all of these molecules. All of these molecules have a negative charge carried on carbon and oxygen, so we're going to have to use another rule. So now the only other rule that we have to look at is induction. If we have electron withdrawing substituents on our molecule, so electronegative substituents, this stabilizes our conjugate base because it pulls away electrons from the negative charge, making that negative charge more delocalized, more spread out, and more stable. On the other hand, electron donating substituents destabilize the conjugate base because they push electrons towards that negative charge, making it more concentrated and less stable. So let's take a look at these 3 molecules on the right, which we said we'd rank 3, 4, and 5. I've highlighted in yellow the places where I deprotonated, and I've drawn out their conjugate bases below right here. So the only difference between all of these carbonyls are simply just what's on the other side of the negative charge. So for this ketone, on the other side is a methyl. For this aldehyde, the other side is a hydrogen. And for this ester, the other side is a methoxy group. So I want to look at the inductive effects of what I've highlighted, whether they're electron donating or electron withdrawing, and see what that does to stabilize or destabilize this negative charge here. So methyls are electron donating, so they would destabilize our negative charge. Hydrogens are not electron donating or electron withdrawing, so they won't really stabilize or destabilize our negative charge. Methoxy groups are actually electron donating, so these will destabilize our negative charge. So I have 2 electron donating groups, so those are going to be ranked last. I have a group that's not electron donating or electron withdrawing, so I'm going to go ahead and rank my aldehyde number 3. Now I want to look between my ketone and my ester. Between a methyl and a methoxy group, which one is more electron donating? I'm going to say it's the methoxy group, because if we look at this oxygen here, this oxygen has a lone pair that can actually resonate, and I'll show you what that resonance looks like. So resonance is pushing electrons closer towards this negative charge. This is destabilizing our negative charge because it's making that negative charge more concentrated. So since the methoxy group is a lot more electron donating than the methyl, which does not have a lone pair that can resonate, I'm going to say that this is going to be a less stable conjugate base, therefore a worse acid. So I'm going to say this is number 5, and this is number 4. So looking at our remaining 2 molecules, we have to look at inductive effects of what's on the other sides of where we deprotonated. On our first molecule, we have 2 methyls, and on our second molecule, we have 2 methoxy groups. Since methoxy groups are more electron donating than methyls, they will further destabilize our conjugate base. So this molecule will be ranked number 2, and this will be our number 1. So we've ranked all our molecules by acidity now. Please let us know at the tutoring center if you have any other questions. We'd be happy to help. Have a great day, guys.